Okay, so now that we've defined some of these examples, we can start talking about how Newton came up with his laws of motion. Okay, so Newton's first law is a pretty simple idea. Okay, it says, let's imagine an object. So again, we'll go back to our trusty box. Okay, in this box, we'll make up a number. We'll say it has a mass of some units. Let's see, say 2 kilograms. Okay, now Newton's first law basically tells us that this object will say, if it's starting with no velocity, so we'll say it's at rest. Okay, how do we change that? Well, if I want to make it move, okay, I have to push on it, right? So to move the object, okay, I have to apply a force. Okay, that's easy enough, right? I have to apply force if I want this object to move. Now, at the same time, what if the object was already moving? What if we had the same object, and this time it was already moving? Well, to change this movement, so in other words, to slow it down, or speed it up, I still have to apply a force. Okay, so essentially Newton's law could be summed up in saying that to change the state of an object's motion, there must be a net force acting on it. Okay? And when we say net, what we really mean is some number, a total, not zero. Another way you'll see this, and it's written like this in the book, is an unbalanced force. Okay? Meaning that when I do the superposition and I add up all the forces, I do not get zero. For example, in the first example up here in the blue picture, what forces are acting on it? Okay, so if we draw the circle around it, the floor is contacting it. Now it's not moving, so there's no friction. But there is definitely a normal force, and there's definitely gravity. But since the object's not moving, these two forces must be canceling each other. So how do I move the object? I have to apply an additional force that does not cancel with these objects, and that will make it move. Same thing in the yellow. Now it's already moving. That doesn't change the fact that it's touching the surface, so it has a normal. It also has gravity. Okay, maybe there's friction, maybe there's not. Let's just say there isn't for right now. How do I change the way this is moving? I have to apply a force that goes unbalanced to this object. And by applying this unbalanced force, I will change how it moves. That is Newton's first law. Okay, so basically, and this is kind of a more direct way of saying it. So an object at rest stays at rest. Okay, or an object in motion moves at a constant speed and in a straight line okay, unless acted on by an unbalanced force. That's first law. And then second law quantifies this idea of force. Okay, Newton's second law says the net force on an object, so the net force on an object depends on the object's mass times its acceleration. A more direct way of looking at Newton's second law is not usually written in this form. It usually is said that the acceleration, or rather how the motion of the object changes, right? Remember, acceleration is change in velocity. So acceleration tells us how the motion is changing. This change is proportional to how much net force is acting on it, but inversely proportional to how much mass it has. In other words, the heavier the object, the more massive the object, the more inertia it has, the harder it is to change the motion. So a large mass means a small change in motion. A small mass means a large change in motion. A large force means a larger change, and a smaller force means a smaller change. So this is essentially Newton's second law. Okay, but typically the way you'll see it written as we apply it is that net force is equal to mass times the acceleration. Okay, and the last thing we're going to talk about in this video is something we use to help organize the forces called free body diagrams. Okay, so one of the things we have to do before we do free body diagrams is we have to have a way to identify forces. Okay, so one of the ways we do that is let's start with a force vector F. Now, typically you'll see a subscript, and in that subscript is where we will label the type of force. So, for example, D for drag, a F for friction, a T for tension, N for normal, and so on, like G for gravity and things like that. Okay, so now what we want to do is we want to look at these forces and let's apply it to an object. So let's say we have a box, it's moving to the right, and we want to identify the forces on this box. So if it's sliding on a surface, it definitely has friction. So we have a force vector with a subscript of F. It has mass, so gravity will definitely be acting on it, so gravity's pulling it down. And since it's touching a surface, it should have a normal force, a force perpendicular to that surface, pushing up. Okay, so that's all the forces being identified inside of our circle. So what the free body diagram does is it eliminates the picture and it focuses just on the forces acting on the object. So we start by drawing a dot which represents our object. Okay, and this could be anything, and that's the important thing. Don't focus on the shape or details of the object. The dot is an object. And on that object we have the force due to gravity. We have a force due to the contact with the surface, that's the normal force. And we have a frictional force pointing to the left. Okay, and that's it. That represents our free body diagram. Now, the next video will go into an analysis of what to do with that diagram. But for now, that's the main idea, is how do we take a picture and simplify it down into just the forces that are acting on it. Now, the other important thing about your free body diagram is that the length of the vectors matters. Okay, remember, the length of a vector is what we call the magnitude, and the magnitude would be like the strength of the force. So, let's look at an example. Say an object sliding on a rough surface, and let's incline that surface, is slowing down on its way up the incline. Okay, so from here, let's make a free body diagram. Now we'll start with a picture. The object's on an incline, it's moving up the incline, and it's slowing down. So that means the net force has to be pointing down the incline, but we'll hit that later in more detail in the next video. So let's start with our forces. So the first one, which should always be obvious, is gravity. Gravity is always pulling it straight down. It doesn't matter the shape of the ramp. Gravity is pulling it straight down. Okay, now normal force, remember normal again is perpendicular to the surface. So since the surface is inclined, the force itself would be tilted so that it's perpendicular to that incline. So since the size of our vectors matter, we need to be careful as we draw these. So you'll notice that the gravity vector makes a little bit of a triangle, and we need to make sure we draw the yellow gravity line in such a way that the part of the triangle that lines up with the normal force is roughly the same size. Okay, because since it's canceling, the box is not moving off the ramp, these two forces have to be equal in length. Okay, and since it was moving up the ramp, there's also a frictional force going down the ramp. And that's the essentials of drawing a free body diagram for an object. So let's do another example. So in this case, we have an object that we'll say is moving to the right because we're pulling it that way. Okay, the object has mass, so there's definitely a gravitational force acting on the object. It's touching a surface, so there's definitely a normal force. Okay, and since it's sliding on a surface, we'll also say it has friction. Okay, so when we make our diagram, we're going to put all the forces on there, and now let's say that it is moving to the right. Okay, so we've got the pulling force to the right and friction to the left. Okay, now you'll notice I made the friction line a lot longer. So that would mean that since it's moving to the right, but friction's a stronger force, it would have to be slowing down. Okay, now there's a couple other ways we could have done this. If I drew the force pulling it to the right as a longer line than the friction, then that means there's a net force to the right, and I would be speeding up because the net force is in the direction of my movement. Okay. Now, if you're curious as to, from the picture, how do we know which way it's moving, remember friction is always against the motion. So if we pointed friction to the left, we had to be moving right. Okay, and another case would be if you make the friction force and the pulling force the exact same length. Now, there's really no way to tell the difference of whether or not it's moving at a constant speed or it's at rest. So the free body diagram does not give away its type of motion, but how that motion changes is what the diagram can tell us. Okay, now that was just along the x-axis, but if we look at the y-axis, it's the same thing. If I had a gravitational force that was bigger than the normal, well, that honestly wouldn't happen, but let's just say for the idea of these two forces, then I would conclude that it would have to be moving downward. Now, of course, if it's touching a surface, you can't be moving downward, but let's just hypothetically say two forces, the bigger one on the bottom would imply that's my net movement. Likewise, if the one on top was bigger, it would say it's moving upwards. Well, this is why you would never see a diagram like this with the normal force, with only a normal and only gravity being different lengths from each other, because that would imply that it's moving either in through the surface or it's moving upward from the surface. So it would never happen. The two vectors would have to be equal in magnitude. Okay, and again, if they're equal in magnitude, the only thing we can tell is moving at a constant speed or it's at rest. But in the case of normal and gravity, it would have to be at rest.